Hello, lovely human. Jen Foxbot here. So, what is a logic gate? How do computers store and communicate, transmit information? All right, in the first video, we looked at analog versus digital signals. Analog is continuous, that's how the world that we live in works, but computers are digital, so their signals are either on or off, or we could say they're binary, either the number 0 or the number 1. Different ways to represent the same thing. So we looked at a simple representation of a NOT gate, which takes an electrical signal and it reverses it. So if our signal is off, then the output of the NOT gate is on. And if our signal is on, then the output of the NOT gate is off. Boom. So in this video, let's take it a step further and look at an AND gate. Maybe if we have time, we'll also get to an OR gate. And if we don't have time, I'll make another video. Hey, there we go. We'll see how fast I can do this and how verbose I decide to be in this video. All right, so let's build a simple AND gate, and then we'll dig in to how it works and how we use the AND gate, the AND logic gate, to represent information in the real world using electricity. Okay, so I have my output so that we can see how the electricity is behaving. And I have a green LED here, and I'll just show you what it looks like. Yeah, look at that, our LED is on. Okay, cool. But now I need to build an AND gate, and we'll use these simple push buttons. Typically, logic gates are built with transistors, and transistors are special because you can use electricity to switch a transistor on or off, whereas these push buttons require my energy to switch them on or off, but that's okay because it makes building them a little bit easier. Okay, so an AND gate requires both inputs to be on for the output to be on. All right, so let's think about that. Both inputs have to be on for the output to be on. In other words, if I translate that to my push button, for the light to be on, I have to push down both push buttons. So what this looks like from a circuit perspective is two parallel circuits. Oh wait, hold on. Okay, we're just gonna connect. We gotta connect the ground, so we'll do that, and then we'll run positive through. Wait, both have to be on. Oh, I lied. It's not a parallel circuit. And props if you caught that. I was thinking of an OR gate. Okay, so this means that we have to force the electricity to go through both push buttons to turn the light on. So, for example, actually I feel like I should move these so you can see this a little better. We'll flip them to the other side. There we go. All right, so if I press one button, nada. If I press the other button, nada. But ready? Dun dun dun. I wired this correctly. Haha, there we go. Yay, button. So an AND gate, both inputs have to be on for the output to be on. So we can also represent this using what is called a truth table. I can't write upside down, so I'm going to write it down and we'll talk about it. And then I'll show it to you just in case it's helpful. So in this case, for this logic gate, we have two inputs, and again, two fingers. Our inputs are push button, we'll call it push button A and push button B. All right, so I write on my table A and B, and we have one output signal. And so for that, I'm going to write output in this third column here. All right, so if I am not pressing either button, both inputs are 0, and the output is 0. I'm going to need to, I don't have enough rows here, but we'll just make it work. Okay, so then if I press button A, then that button is on, and that gets a 1. If button B is not pressed, that gets a 0, and the output is 0, like so. Likewise, I can push button B down, and that gets a 1. My button A is not pressed, so that gets a 0, and my output is still 0, like so. Oh, look at that, so sad, they're all 0. Okay, but hey, if I push button A and button B, now we have both inputs are on and the output is on. Yay! Ta-da-da-da, there we go. All right, so that's why it's called an AND gate. Both inputs must be on for the output to be on. And here you can see if we trace the path of the electricity, we have the ground is connected, yay, ground, or the negative side of the circuit. In this case, that's applicable. And we have the positive, energy is flowing from the positive side of the battery through this wire. When I push this button down, energy can flow out out the other side of the push button through the yellow wire to the second push button. And then the electricity can flow from the yellow wire through the push button to this red wire and complete the circuit, and our light turns on. Yay! So this is a series circuit. There is one single loop for the electrical current to flow. We could also build an OR gate. Hey, we are going to get to it. I think we do have time. And an OR gate, either input, either A or B, can be on for the light to turn on. So let's flip our approach. Let's write our truth table first. And while we are writing our truth table, I want you to either actually try to build the OR gate on your own because you're a smart cookie and you can totally figure it out, or at least think about it, or even better, draw a picture. What do you think our push button circuit will look like? And if you were paying close attention earlier, I kind of gave you the answer earlier because I mixed up and or. Okay, but let's take a gander at what our truth table is. Okay, so an OR gate. Well, first we got to start with if no button is pressed, both are 0, then well the output is still 0. If A is pressed and B is not pressed, then the output is 0, like so. So these are our first two rows. Okay, and then if we can flip A and B and not press A and press B, so A is 0 or off, B is 1 or on. Oops. Oh my goodness. Oh, my brain. Okay. I'm recovering from being sick, so my brain is a little sluggish today. So just kidding. If either A or B is pressed, then our output is 1. My bad. I gotta fix that. So this should be 1. And props if you caught that. I'm testing you, right? Hey. Okay. I make mistakes all the time. Mistakes are totally okay. It's important to acknowledge them, and if you can, catch them. And then you learn from them, right? Okay, so life lessons with Jen Fox1. Okay, so then if A is pressed, if I press both buttons, what do you think will happen? The output is on. All right, so that is our OR gate. I should probably label this. OR gate. Da, 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 da. There we go. Yep, OR gate. So if either A or B is pressed, then the output is on. Okay, so now that you've had some time to think about how to build it, and if you haven't, go ahead and pause the video and come back to it when you want to check your answer. Okay, so we are going to stick with our 2 push buttons. You got to connect to the negative side of the circuit. And in this case, we have 2 parallel loops. So there are 2 paths for the electricity to flow, either through button A or through button B. And so this is the one I was like, yeah, let's build this earlier because I love parallel circuits. Wait a second, that's the AND gate. Okay, so how do my fingers go? Okay, so button A pressed, light turns on. Button B pressed, light turns on. Button A and button B pressed, light turns on. There we go. Da 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 da. All right, so fun. So these are the simple logic gates built with push buttons, but you can do the exact same thing with transistors. It works with, if you want to get technical, it works with BJT transistors, and it also works with MOSFETs. If you want to cascade the transistors, MOSFETs are better for that. And if you're like, what? My eyes just glazed over at those words. No big deal. Oh, am I going to do another book plug? You can learn more about it in my book. Hold on. It's behind me. Da, 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 da. If you are curious. If you have specific questions, I can make another video as well. Okay, so how does this actually help us store electricity? Yeah, right? Great question. Or not electricity. How does this help us store information? How do we use electricity to store and transmit information? Well, like I mentioned, you can use transistors to trigger other transistors. You can use electricity to trigger other transistors. So basically, you can take these simple building blocks and combine them together to build more complex circuits. This is how you get to a simple calculator. Super cool. Now, we're calculating in binary. We're adding binary numbers, so zeros and ones. But you can do it. You need a lot of these, and actually, that's the kind of capstone. Oh my gosh, I'm so bad at this. Capstone project of my book is to build a binary adder. Super cool. So that's kind of how we do it. And my favorite thing is that the hardware bits and pieces are where all the software comes from. So if you've ever written a line of code, you've probably come across, you've had to type, if this or that, or if this and that. That's where this comes from. So cool, right? So the software is built on top of logic gates that actually are and or not, and some more complicated logic gates. It's so fun. I love this stuff. All right, I hope that that was useful. Please let me know if you have any questions, and feel free to make requests about other types of fundamental circuit shenanigans that we can get into. Thanks for watching, friend. We'll see you next time. Bye.